All right, welcome. I'm excited to give everyone a 30,000-foot overview of the schema of the data warehouse. We're just going to get into won't have time today to get into the nitty-gritty details, but I think we'll be able to cover the highlights. And in terms of looking at the nitty-gritty details, I do want to just kind of provide some links here. These are resources that provide a lot more information about the data warehouse in terms of the design, the schema, etc. You can see this link here that I provided. Let me just show you what that looks like. This is the web page that you would arrive at if you clicked on that link. It's got quite a number of documents here. The ones that I'm going to be focusing on today are the core schema, the tool agnostic core schema is primarily what I'm going to talk about today. But if you come back and you peruse these later, you might also be interested in the process dashboard specifics. And then the third document that might be interested, if you'd just like to know more detail, is the schema plan. The schema plan basically provides some of the design rationale that went into why the database is structured the way it is. So, but let's see. But as I mentioned, the core schema is mostly what I'm going to be talking about today. Almost all of the information that I cover in this presentation is also in the core schema document in a lot more depth. So just moving on, I wanted to start off with a quick background piece of information, which is what is the data warehouse? And a lot of us in our software development careers have done work in relational databases. And it would probably be a safe guess that most of the work that we've done as developers has been in transactional databases. Transactional databases have to support a mixture of reads and writes, mostly on individual rows. So like if you were writing the transactional database behind Amazon, you would have reads and writes for orders. And like when somebody placed an order, you'd create a row for that order, and you might create a row like rows for each of the products they bought, the quantities. But most of the reads and writes are on individual rows, and of course we have to organize those rows carefully to make sure that we don't have to lock massive portions of the database to make updates. So the best practice in transactional databases is something like third normal form to avoid data redundancies and streamline atomic writes. But what you find is that these sorts of transactional databases don't provide very good support for data mining. And I'll give an example. Like if we think about Amazon again, when you're browsing around in Amazon, you might see a page that says, people who viewed this page ultimately ended up buying, and then it provides links. Or it's like, people who bought this also bought this. Now, Amazon's got to come up with the answers to those two questions in like a few milliseconds so that it doesn't take too long for the page to load and you don't like get fed up and go to another online merchant. And so if you can think about the traditional transactional databases that we've all built in the past, trying to look at one of those databases and run a query and come up with an answer that says, people who bought this usually bought this too, or people who viewed this page ultimately ended up buying. Transactional databases don't answer those questions quickly. And so warehouses, on the other hand, are optimized for the exact opposite use case, data mining and analysis. And unlike a transactional database where there's a mixture of reads and writes, warehouses, typically you write a piece of data once and then you read it millions of times. So it doesn't matter how hard it is to write it. You really want to optimize everything for read speed. And then the other part of data mining and analysis is that most of the reads that we do in a data warehouse touch millions of rows. And we want that to be very, very fast. And so there's been, decades of work by talented people in this field who have come up with a set of best practices for warehouse design to support these types of data mining and analysis. And those best practices kind of come under the name of dimensional modeling. So dimensional modeling is a series of design practices that we use to create a warehouse that can be fast and scalable. And some of the things that I'll be talking about in this presentation, but I just want to cover this terminology. These are the key parts of dimensional modeling. One is fact tables. A fact table contains rows that represent fine-grained measurements or observations. And then separately, there's something called dimensions. Dimensions are tables, and the rows in a dimension table hold adjectives that facts can use to describe themselves. Okay. And then these two things fit together in what's generally known as a star schema, which would be a single fact table that has pointers to all of its descriptive dimensions. So let's just, I'll show you an example here. Here's an example star schema for something that we're all familiar with as TSP practitioners, the time log. Okay, so in the center of this table, we have a fact table, which I've drawn in blue. The fact table is the fact table for time log entries. Each row in this table is one time log entry. Now, there are some attributes that a time log entry has, like the date that the timer was started, how many minutes of time have elapsed, how many minutes of time were of interrupt time there were. So those are simple numbers that would be present on the row in the table, the database table for the time log. Now, all of these other things around it are dimensions. Who was the person who recorded this time log entry? What team were they a part of? What project was this for? Within that project, what component and task were they working on? And what was the process phase for that task? Now, each one of these things is a dimension, which means it's stored, each one of these is in its own table. There's a project table, there's a person table, there's a process phase table, et cetera. And the time log entry basically describes itself by including a foreign key to each one of these dimensions. So you can see I'm pointing to 6 different dimensions here, which means that my time log table would have 6 columns. Each of those 6 columns would be a foreign key to one of these other tables. There'd be a project column, which is a foreign key to the project table. There'd be a team column, which is a foreign key to the team table. Now, so this pattern provides a great deal of power for data mining, because when we're doing data mining, most of the analyses that we perform, we start by querying a fact table and adding an aggregation clause, like we're either counting things or summing them up. And then we filter our query using one of the dimensions. So as an example, if I did an unfiltered query, I could sum up the total amount of time logged by every project in the warehouse. I could just say, select sum of elapsed minutes from time log, okay? And maybe a second later, I'd get a number back, and that's the total number of minutes of time log entries in this warehouse. But then if I just add a group by clause and add in the project, now the results I'm going to get back are going to give me a list of all the projects in the database and how much time was logged against each of them. Okay, so I've just done a completely different analysis just with a simple group by clause. Now, if I were to add one more thing to my group by clause, I were to add the process phase, now I'm going to have project and process phase as the keys and the amount of time. And so suddenly I can do cost of quality metrics, right? Now, or if I were to jump back up to my top level query, and if I were to group by team and then count the number of people, then suddenly now I've got a report that shows the number of active members of each team, people who actually weren't just in the plan, but they actually logged some time, right? Or if I were to group by the start date and by the person, now suddenly I've got a report that's telling me the actual direct time per week. So you can see that this simplicity of this schema is that just by choosing which things you add to your filter or group by clauses, you can do just a vast number of different analyses. And the great thing is that all of these queries are super fast because they can be optimized using the the indexes that the database is built on all of these primary and foreign keys. And so databases are super optimized to do smart, intelligent things with indexes. And so all of these queries can be very, very fast. Okay, so this is what we typically call a star schema. Now, there's another terminology in data warehousing that is called a snowflake. And so, and I just want to give a demonstration of that. So I'll go back and forth between these two things. This was our star schema, and then this is our snowflake schema. The only thing that's different, I've still got project component, task, and process phase, but I've added a little bridge dimension in between here. In this case, I've got a plan item dimension whose rows represent the distinct tasks in a project plan. Okay, so every task in a project plan belongs to a specific project. It has a task and a phase, and it's part of some component. But now my time log entry has a single foreign key to the plan item table, and then the plan item to a row in the plan item table representing an item in some project plan. And then that row in the plan item table has the foreign keys to these other things. So this pattern called the snowflake still has all the same speed and query flexibility as the star schema. It's just a different way of capturing things. It makes some tasks easier. I won't get into it in too much detail here, but I just want to make sure that we all are familiar with these terms, star schema and snowflake. Any questions about that so far? Okay. So now you kind of have an idea of how the tables are related. The next thing we would be curious about is to step back and see what the entire database looks like. Now, when we're doing a transactional database, the way we typically do that is with an entity relationship diagram. And one of those is available for the warehouse, but I will just tell you that I would never use it. It's not the best way to visualize the relationships in a data warehouse. Okay. So how do you visualize the relationships in a data warehouse? You typically do it with what's called a bus matrix. So this is like a really simplified view of some of the main fact tables and some of the main dimensions in our data warehouse. So our facts might be something like time, size, and defects. I mean, those are all obvious things that would jump out at us as facts we'd want to capture on a TSP project. And then these are the dimensions: the team, the person who collected it, the project it was a part of, where in the WBS it was, et cetera, et cetera, et cetera. And so then we just, in this matrix, we can show which fact tables use which dimensions. So the time log schema that I was showing you before, obviously it's going to be collected by a particular person working as part of a particular team on a project within some part of the WBS, working on some task associated with some process phase. All of these things are all the dimensions that a time log cares about, time log entry cares about. And so, I mean, we could look at each one of these things and like a size measurement suddenly doesn't care about the process phase anymore, but it does care about some new dimension called size metric. So once again, this is a really simplified, abridged version of the bus matrix. But the key thing is that that basically what we're interested in is what the facts are, what the dimensions are, and how they're related to each other. Now, the other thing that's really useful is to notice that dimensions, many of the dimensions get shared across a number of facts. So like the person dimension gets reused by all of these different facts, or the project dimension gets reused by all of these different facts. When a dimension gets reused across, a range of different concepts, it's called a conformed dimension. And a conformed dimension is useful because then it allows us to join two facts together. So for example, we could start with a component, which is one of the dimensions here, and then we could gather its time, size, and defects, right? And the fact that we've got this one dimension called the WBS allows us to pull together the time, size, and defects for some part of the WBS. which is obviously going to be useful in terms of doing some sort of TSP analysis. Or, and you'll notice there's a dimension over here called date, which I'll get to later. We could start with some date range, and we could gather its planned and actual direct time. And then we would have things like be able to do an analysis like planned versus actual direct time in our embedded chart. So there's a lot of power in conformed dimensions in their ability to help us draw facts together. All right. So moving right along, I want to touch on some of the common dimensions in the warehouse, and there's probably over a dozen dimensions truly in the warehouse, but I'm just going to touch on the ones that are the most important. So the first one, as you can imagine, that I'm going to touch on are the process-related dimensions. So we have a dimension for all of the processes that are known to the warehouse. That it's represented in a database table, and that database table contains a row for each metrics collection framework, like say TSP or process min, or we're familiar with the metrics collection framework concept. And so each metrics collection framework has one row in this table. And then each workflow that a team builds in one of their project WBSs also gets a row in this table. So when you define a workflow in your team project called course module development, then there's going to be a row in the process table with the name course module development. Okay, so moving right along, processes obviously contain phases. So there's a separate table called to hold all the phases that are known to our defined processes. Each row in the phase table represents a single phase in a single process. That row will contain the name of the phase, like, for example, planning, design, design review. It'll contain the process that phase belongs to as a foreign key to the table above. It'll contain a number from 1 to, if there's like 12 steps in the process, it will contain a number from 1 to 12, indicating what order the phase comes within the process. And then it also includes the quality type, which is one of the 4 things overhead construction appraisal or failure. So since there can be many phases in a process, this is a many to one relationship. Any questions about that? Okay, moving right along. The next super important dimension is what I call the plan item. And this is a snowflake dimension. So each row in the plan item dimension captures a single component or task in a project plan. So if you think of any component or task in a project plan, that one task creates a single row in the plan item, or a component creates a single row in the plan item dimension. So those rows in the plan item dimension contain foreign keys pointing to the project that the item belongs to, the WBS element, and I'm going to come back to this in a second. Think of this as the component that the task rolls up into, and then the task under that component and its process phase. If you take a look at this example of a personal process dashboard with somebody working on a particular task, you can see this first thing right here is the project, and then all of this stuff is the WBS element, and then this thing at the end is the task. Okay, so that's just kind of how we would visualize it. Now, I have to offer some apologies, but the name WBS element can be super confusing to people who are familiar with the process dashboard. And yeah, I'm sorry about that. But as I designed the warehouse, it was my most important goal was for it to be tool agnostic. Okay, for the warehouse to not be tied to the process dashboard, to not be tied to the Excel spreadsheet, to not be tied to Microsoft Project. I wanted it to be tool agnostic. And so I went out and did research on what industry calls this concept, and PMI calls it a WBS element. So WBS element is the terminology that PMI uses to describe the hierarchical components that we use for subdividing the project. Now, in PMI terminology, a WBS doesn't drill all the way down to the task level. A WBS is just kind of the hierarchical structure that we use for reporting back to like our customers or management. And tasks don't actually show up in a PMI WBS, just these like roll up things. So the way that we would map that to concepts that we're familiar with, if you were using the Excel spreadsheet from the SEI, the TSP spreadsheet, you had a SumS tab, and the SumS tab captured assemblies, and I guess parts. So I can't remember what the difference between was, but a SumS assembly is basically would map into this WBS element concept. And if you were looking at the process dashboards breakdown structure, you'll know that we generally build a top level thing out of components, which are little square things, and then we create tasks underneath them. And so the components are what get translated into WBS elements, and then the tasks underneath those are tasks. So that's the distinction. So as long as we're all familiar with that and we don't trip over the word WBS element, then we can keep it. Okay, so there's another concept, another important Snowflake dimension called data block. A data block is conceptually some collection of data that was gathered by a single person acting as part of a specific team within a given organization. Now, I'll give two real world examples of it that we can appreciate. One is that when you're in the process dashboard and you click the export my data now menu item, it bundles up all of your personal data and it writes it out into the team area as a P-dash file. And so there's a P-dash file that's associated with you working on that project, and it gets written out into team area. That P-dash file would then become a data block, or there would be a data block in the warehouse to represent that P-dash file. Similarly, if you were using the TSP spreadsheet, Excel spreadsheet from the SEI, each person on the team has one spreadsheet that they're using to capture their actual data, their defects, et cetera. That spreadsheet would be a data block. And so the data block dimension would have a row in it for each one of those real world things. And then that row would have pointers to person, team, and organization. And I think the main reason that the data block was actually created is because when we're loading the warehouse, especially if we're loading it over time and it's already populated and we get new data. Let's say we get a new Excel spreadsheet from somebody and we want to load it into the warehouse. It's pretty critical to know which things in the warehouse are getting replaced with this new spreadsheet, which rows are no longer up to date because they've been replaced by the data in the spreadsheet. So tying all the things that came from a single spreadsheet into a data block makes it easier for the loading logic to find those things and update them. All right, any questions?
这是有限的 What information included in organization?
Great question. So when I built the warehouse originally, I knew that we would someday want to be able to keep track of, or ideally we'd want to be able to keep track of different organizations that had so for example, maybe that had submitted data. If we had a data warehouse that was as big as the entire world, then theoretically we might have organizations in it representing, say different companies that used TSP. However, we're not there yet. This is an area where the warehouse design is actually 12 steps ahead of the data that we're actually gathering. At some point, one of our goals as a data warehouse working group is to go back and look at some of the metadata that was gathered by the SEI on things like industry segment, like, for example, whether people were working in online retail or embedded or military or pharmaceutical, medical stuff, which industry segment they were, trying to like go back and find some of that metadata from the projects that were collected, and then try to backfill that into the database. If and when we get around to doing that, we will use the organization dimension basically as a way of tagging different
Mm.
data in the warehouse as having come from an embedded system or having come from um, a DoD project or something to that effect, or military. But at the moment, we don't have any of that data. So if you were to look in the warehouse right now, the organization table has one row in it with the name all organizations. And so
Mm.
it doesn't have any more detail than that. It's not currently populated.
Okay.
Great question. Okay, so moving right along, that covers the main dimensions. And so now I want to talk about some of the bigger, more important fact tables that we might be interested in looking at. The first one, I kind of showed an example of it before, which is the time log uh, fact table. Now, the time log fact table points to the two snowflake dimensions that I just covered, the plan item and the data block. Um, so once again, the time log fact, uh, each row in the table the table has columns that include stamps for the start time and the stop time of that time log entry. It includes a column to hold the delta minutes, holds a column to hold the interrupt minutes. Then it has a column with a foreign key to a plan item, indicating which project plan item this time log entry was logged against. And then, of course, from that plan item, that pointed to the plan item, we can look in the plan item table and get pointers to which project, WBS element, task, and phase it was associated with. Similarly, the time log entry has got one column, which is a pointer to the data block table. And that then if we were to traverse that and look at that row in the data block table, we would get pointers to the person who collected this time log entry, what team they were working on, and what organization they were part of. Now, when I do the time log schema before, I drew it all in a circle so that you could see how the snowflake was how it looked like a snowflake. For the purposes of just trying to make everything fit concisely on this slide, I didn't draw it in a circle anymore, but it's still the same classic snowflake schema. Any questions about that? No. And at this point, I think now that you understand how fact tables and dimensions work, it's almost like intuitively obvious what each one of these fact tables is going to look like. So when I show you the defect log fact table, once again, each row in this fact table represents a single defect log entry. And so a single defect log entry has got some attributes to it, like the date that it was found, the number of minutes of fixed time that were, whether or not this is a fixed defect, and the ID of the fixed defect if there was one. And then there's something that I've also included called a fixed count, which is almost always the number one. But there are some times when, like say, somebody finds 12 different semicolons, missing semicolons, the compiler finds them. Rather than pressing the bug button 12 different times and typing it all in, it lets them put the number 12 in the fixed count column and say, yes, there were 12 missing semicolons. And so if there were multiple identical defects, then the fixed count will hold a number greater than one. Most of the time it's just one. And then there are foreign keys that point to these other dimensions. Just like the time log, we've got a foreign key pointing to the plan item that this defect is associated with, the data block for the person who logged it. And of course, from those things, we can get to the project, WBS element, task, person, etc. Now, also, we're familiar with the defect types that we used in PSP, which were things like in the PSP class from the original book, there were numbers like 10, 20, all the way up to 100. Sometimes in the dashboard, people prefer to use these instead of the numeric representation, they prefer to use a textual representation like syntax, function interface. Those things are stored in a defect type dimension, right? So we have a dimension that holds the different defect types that are known to the system. And then this defect log entry can just point to one of those. And then finally, there's going to be two different columns in this defect log table. One column holding a foreign key to the phase table where the defect was injected, and one with the phase it was removed, process phase. Okay. All right, no questions. I'll just keep moving along. Size rounds out our TSP trilogy, time, size, and defects. And so once again, a size entry contains a row in this table contains floating point numbers for base, added, deleted, modified, reused, and total. And it also holds because we are almost always interested in added and modified, and we don't want to require people to add these two numbers up every time they do a query. It redundantly stores the sum of added and modified in its own column, just to make things simpler for us as query builders. Once again, it includes foreign key plan item in the data block, but then it also includes a foreign key to the size metric dimension. So the size metric dimension holds the different size metrics that are known to the system, like lines of code, text pages, slides, whatever. As we know, teams can define their own size metrics in the latest version of the dashboard. And so those would create new rows in the size metric dimension. And then finally, it contains a pointer to something called measurement type, which the two main measurement types are plan and actual, which means that when we have planned and actual sizes, like the planned size will be written into one row of this table, and then the actual size will be written into a second row. Instead of having columns for planned size and columns for actual size all in one row, we put them in separate rows. The reason for this is that there's actually more than just two types of measurements. Perfect example is that if somebody used probe to come up with it to create their estimate, then there's also an estimated proxy size. So that would create a third row in this table. Well, why do we care? Well, because when you're doing the primary difference between probe method A and B is which of those two things you put on the x-axis. So yeah, we need to store them separately.
David, Jeff.
Yeah. Yes.
What happens? You said as you pointed out, people can define their own
Size metrics.
What if they use the same name but they had different definitions
of size metric?
Yeah.
Great question. Not a problem that I can solve, but I mean, we would have to take a look at that. So for example, if people had different definitions of a line of code, then it might be hard for you to take the data from two different organizations and compare apples to oranges. But I think that was already true, and it's not a problem that magically disappears because you've got a data warehouse.
Yeah. I was thinking more of the non-standard size metrics teams might come up with, where two left-handed red kumquats have different meanings.
Yeah, great question. I mean, all you can do is take a look at it and see if it came from two different teams, then maybe it's not a good idea to add it up. The team concept in when I'm loading data into the warehouse, I create one team for each team dashboard that I load. So if you're loading a particular team dashboard and it's got 96 projects in it, those are all part of one team, quote unquote, in the warehouse. So so maybe one of the things, like you're saying, especially if there's non-standard size metrics, would be to take care when rolling up size data across teams, because you might get burned.
Okay, just to be clear, I think there are already different definitions of line of code. For example, line of code versus C versus Ada, or using different counting standards. So it's already an issue.
Yeah, agreed. Okay, so let's move on. The next fact table that I want to talk about is called task status. Oops. So the task status fact table, because this is one that I use a lot in my own analyses. It includes one row for each assignment of a leaf task to an individual. Okay, so it's almost like the assignment of a task to a person, and it's kind of pulling together several important concepts here. So a task status has got the estimated time that that person planned to spend on the task in minutes, the total actual time they spent on the task in minutes, which we could have gotten from aggregating the time log, but it's included here to like make it so we don't have to do as much work in our queries. It's also got the date and time the work was started, and the date and time the work task was marked complete. If it was marked complete, might be null, right? If the task is still in progress. So then we also have, once again, foreign keys that point to plan item and data block to indicate, which task we're working on and who this thing is assigned to. And since I mentioned that this is a row for each assignment of a task to an individual, if there's a task in the WBS, for example, that's assigned to multiple people, this table would include a separate row for each person. Any questions? Okay, so moving right along. Once again, those are probably the four most significant fact tables. There's a lot of others, but I won't get into too much detail here. Just want to hit the highlights. So I want to talk about a couple of key relationships too that are super important to understand. The first one is something called a process enactment. So you remember how we do something like the PSP class, and at the end of the PSP class, we've got this nice little trend chart that shows the 10 programming assignments we've done, and there's a data point for each one. Well, that's great when you're in this nicely structured class where you've got 10 things that all happen in a row. But when you step out into real life and you've got these project WBSs with this big sprawling hierarchical structure, then a person like me who writes tools says, well, where are the data points? Where do I look into this big hierarchical thing and pick out a data point that I can put on a trend chart? And so the process enactment table is what comes to the rescue here. A process enactment is a single instance when a process was used to plan and or do work. In the word enactment, I've provided the definition here, the process of acting something out. So each time you select a component in the WBS and apply a workflow, you haven't created at that place an enactment of the process. Okay. And so as an example, I can show this component ABC. Somebody applied a workflow that had these steps: plan, design review, code review, test, and postmortem. Those were the steps in their simple development process. And so all of the things in this little curly brace create an enactment of that process. Now they went and they put some follow-up task after it that didn't come from the process. So that follow-up task is not part of an enactment. It's just a random plan item floating around. Okay. Now, when you apply a workflow to a component in the WBS lets you modify and tailor things. So, for example, when this person did component XYZ, they decided they didn't need a design review step, and they decided that they were going to break code into coding of module foo and coding of module bar. And so and then they're going to continue with the code review, test, and postmortem. So they've heavily tailored this particular enactment, but it's still one enactment. It's one place where they applied the workflow to the WBS and then possibly made changes. Tailoring does not break the enactment. So why this is important is because the dashboard or other tools would look at each one of these enactments as kind of a coherent thing. When we finish all of the tasks in a single enactment, that single enactment can become a historical data point that we could add to a trend chart, or a scatter plot, or we could sum up the data in it and use it to assist in the planning of future work, like percent time and phase, or cost of quality, or estimated yield, etc., estimated productivity. Does that all make sense?
I got a question for you.
Okay.
Up to this point, you've been talking about fact tables and dimension tables.
Uh-huh.
process enactments,
I would call
in
process enactment a fact table.
a fact table?
Yeah, it
Uh,
mostly aligns, it most closely aligns to the fact table concept. Yeah. So
So does it have contents like you just showed in the others where it has a foreign key that points to a WS element and foreign key
yes,
points to process? Okay.
yes, and I'll show that on the next slide.
Okay,
Julia.
sorry.
So do we need to include language that the Agilists will understand as well? Like this is very, like I understand it, but like, I mean, should we also say swim lanes versus just process phases? Or, is there any need to make sure that
Yeah,
Agilists will understand it?
I think that is a great question and something that maybe Brad should add to his list for any stuff that he's going to be creating. And like I'll point out that swim lanes are even a little bit. You've got to be careful there because oftentimes the swim lanes in a board might be waiting, selected, in progress, done. Those are not like process phases, right? They're like approval phases in so or ready for test or something. So even just using the word swim lanes is problematic.
Yeah, yeah, I understand. I just want to make sure that, yeah, I understand what you're saying.
Okay, a quick comment here. Uh,
Yes.
in the DevSecOps world, the process phases are actually respectable again. So you actually will start to see things like the build, the test, and so forth. It's what goes around comes around. So we have to be a little careful in how we want to be able to talk to the different. We want to be able to talk to the different groups, but we want to be careful we don't lock ourselves into a particular language because, as I said, this is coming around again. Uh, if we want to talk to the Agile folks, the process enactment is not all that different from what they would conventionally do in a story that has swim lanes.
And the phrase that I've seen some of the coaches in our community use is to reach out to the Agilists and say that this is the definition of done. So these are the pieces of our definition of done. We've got to have all these pieces checked off before we consider that this component is done.
Indeed,
And
many of them do have tasks as they complete through, and they may or may not show up explicitly on their swim lane.
yeah, okay. So Brad had asked about the columns, and so I'm going to show you what the process enactment looks like. So it's mostly like a fact table, but with three columns. The three columns are the root of the enactment, the process that was applied to that root, and some plan item that is now part of the enactment. So from this example I showed you before, we had component ABC and it had these plan through postmortem. So here's how that would get stored in the database. And I'm drawing this with pictures, but what you would actually see if you looked in the database would be three numbers. These are all foreign keys pointing at, this is a foreign key pointing at component ABC in the plan item table. This is a foreign key pointing to the simple dev process in the process table. This is a foreign key pointing to the plan task in the plan item table, right? And so, but if you think about this, how this all plays is that there is a compound key of the enactment root and the process that was applied to it. And then for that compound key, there is one row for each item that is included in the enactment, including the root, which is, oops, sorry, shouldn't have clicked. That's important. The root node is part of the enactment. And that's important because people will often record size metrics or something on this root node. And so if you're trying to sum up all the data out of an enactment, you want the root to get included. All right, questions about this? Okay, moving right along then. Process phase mapping is another really important concept because processes do not exist in a vacuum. They're often related to each other. So here's an example. in the PSP, when we taught the PSP class, we might have had, obviously these are like abridged phase lists because I don't have enough space to put them all on the slide, but PSP1 had phases of design, code, compile, and test. PSP 2.1 had phases of design, design review, code, code review, compile, and test. And then TSP adds design inspections and code inspections, etc. Now, these are three different processes: the PSP1 process, the PSP 2.1 process, the PSP process. But when they're related and we collect data with one process, we would often like that data to roll up into our analyses for another process. So here's an example. When we get to the end of a PSP class and we show a trend chart of the productivity or yield and how it's evolved over the course, we would like that trend chart to include all 6 to 10 programs that the person wrote, even though that data was collected with several different versions of the PSP process, right? And then similarly, if someone used on a real life project, if someone used PSP 2.1 to write a module, then we would like the code time from that PSP 2.1 process to roll up into their team's TSP analyses into the code phase. Okay? So those are some examples of why we would want data in one process to roll up into data for another process. So these things get stored in a phase mapping table. So this would once again most likely be described as a fact table. It has two columns, which a phase that exists in some process, and then a phase usually in another process, but not that it maps to. So I've given an example here of this table. This is the same data that's being shown in the in this picture on the previous slide. So it's saying that, as an example, PSP1 design gets mapped to PSP 2.1 design. Or here's a better example. If somebody uses a PSP 2.1 task, or if they use PSP 2.1 to write a module as part of a real world project and they log time against design, we want that to roll up into the detailed design phase in TSP on the TSP project plan summary. And so you can see just some examples from the mapping we saw on the previous slide and how that would get represented in this table. Now I'll point out that identity rows are also included in this table. I didn't put them here for brevity, but PSP1 design is the same thing as PSP1 design. So there's identity rows. Now, so why do we care about this? It's because when you look at a plan item or something like a defect fact, anything that points to the phase table, anything at all in the warehouse that points to the phase table, it might point to a phase in some very specific process. Like, for example, a plan item the phase that it points to might be the something in Julia's course development process. Her course development workflow might have a step called review slides, right? And so her plan item might be pointing to the review slide step in the course development workflow. That's all great if we're doing an analysis of the course development workflow process. But if we're doing an analysis of something else, like we're trying to roll it all up into TSP or into some higher level process, then it's important for us to pull this phase mapping to make sure that we're converting the data into the process that we're trying to analyze. So anytime we want to perform a process-specific analysis, it's critical to traverse the phase mapping table to convert to the process. So here's an example. We've got some sort of a fact table. It's pointing at a phase. But this is the process that we're really interested in using for our analysis. So we kind of have to link these things together, put the where clause in this process, and then this is the phase that we want to pull out and use for like rows in our final result. And I'll just give an example. Let's say that a whole bunch of people use the TSP process. If we just tried to like do an analysis to say something simple like the time log and roll up all the time according to the TSP phase that was logged against. Well, if they were using any team workflows, then their time log might be pointing to a phase that's in a workflow. Time log might be pointing to a phase in the workflow. And then that phase has to get mapped to a phase in the TSP process. Questions about that? Kind of a detailed thing, but
I got one.
Yes.
Remind me, does this go both ways or is it just one way? So if I had, if I were looking at a PSP1 design phase and I had mapped it to 2.1 design and a TSP design, detailed design, if I looked at the PSP1 design, would it go out and find data on the PSP 2.1 design and the TSP detailed design?
The it's the in the dashboard, there's an editor that allows people to create these mappings, and it does not. So the editor allows people to create mappings in one way, and then it allows them to swap it around and create and define what the mappings are in the other direction. So those are edited separately. They do not have to map them both ways.
Okay.
The mappings that are created automatically are that by the warehouse loading logic is that all the steps in a team workflow will automatically get mapped to the phases in the underlying metrics collection framework. So I'll build all those mappings for people automatically. And then within a single team dashboard, if there are multiple different projects that all reuse the same workflow, then I'll map those across the different projects. But other than that, people have the opportunity to define mappings and edit them themselves.
Will you have that ability in the data warehouse to be able to do additional mappings, given that we have organization A and organization B that know each other? Can we do the mappings between those two workflows?
That's a great question. I've actually got something in our data warehouse working group, WBS, for us to try to look into that question.
Okay.
Okay. All right. So moving along, I want to just touch on, running out of time, so I'm going to touch on a couple of miscellaneous dimensions that are that show up everywhere, so they're good to know about. One is the text dimension. Real life data often includes free text information like the descriptions of defects, comments in the time log, or the notes attached to a plan item. Now, if we were to put this free text into the fact table, it would cause the on-disk storage of those table rows to be much larger and variable length. And those two things together would dramatically slow queries that have to scan millions of rows. Okay. So to solve that problem, anytime we end up with these free text information, we create a row in the text dimension. And that row in the text dimension has its own primary key. And then we use a foreign key to point to that row. So we're rarely going to use the text dimension in the C data warehouse because almost all of the descriptions and comments, all of the descriptions and comments have been scrubbed. They're not there anymore. So this text dimension isn't going to show up very often in our work, but I wanted to include it in this presentation for people who are doing in-house analysis. Moving right along, there's the date dimension. Many facts include dates, and almost all the time there's a date in a fact table. I store it twice. Once as a database native timestamp, and then again as a foreign key into something called the date dimension. So why do we do this? Another dimensional modeling best practice. Date calculations and conversions are time consuming, especially if you have to perform them for 1 million rows as part of a database query. So to save time, I do those calcs once and store them in a date dimension. As a result, then when people do a query, they don't have to do the calculations over and over again millions of times. So here's an example row in the date dimension. It would have a key that would be an 8-digit number like 2024031. And so then this is that date converted into different formats: US, EU format, month, day, first. This is the day of the week, whether it's a weekday or a weekend, the month, day, month, year, etc. So basically, when you're doing something like a time log, So when in the time log, I showed that it had a timestamp for the time that the time log entry started. I will also include a pointer into this dimension, this date dimension, with basically an 8-digit key. The other thing that the date dimension allows us to do is it allows us to store and distinguish between certain like exceptional date values, like something's not yet happened, something will never happen, something could not be calculated, the date in the source system was invalid. And all of these things would basically show up as a null timestamp, but this dimension allows us to distinguish between them. So some of the ways the date dimension helps us, it allows us to do some fun things. Like if I were to select the max date key for a set of tasks to see when the last one finished. So if I collect some set of tasks and I ask for the max completion date key, if it comes back as a number like this, that tells me that the last task in that set was completed on March 11th of 2024. But if it comes back as a number like this, I know that one of the tasks is not yet complete, and so the set isn't either. And this thing is using database indexes, so it's very fast. And so it's, as an example, how I would find process enactments that are 100% complete. Just join that process enactment table to the task status fact table, and I'm off and running. And these are some other things that you can do with date dimensions, but I won't get into it. They're here on the slide if you want to come back and look at it later. The last thing I want to cover, since we're at the top of the hour already, is auditing. In a warehouse that's got data from a lot of different diverse sources like ours, it's critical to track the provenance of the data. And so there is an ETL batch dimension. A row is created in this dimension for every import operation that occurs, including the name of the file that was imported, the time the import started and stopped, and how long it took. Oh, let's see, the original date that this file was created, like the team that saved it, like when the timestamp when this of the actual real world life project data. The application that loaded this into the warehouse and what version of that software is being used, etc. And then if there was some sort of a problem, like I'm trying to load this data and there is an error that's thrown, then I will create extensive diagnostic information about that error, write it into the text dimension, and then store it here in this text key. Usually this is null, indicating that everything completed successfully. So that's the first part of this is this is the dimension that captures different things that got imported into the warehouse. And then the second part of it, is how this plays out in terms of the fact tables themselves. So when a team submits multiple snapshots over time, like at the beginning of the project and every week, maybe at the end of their project, the warehouse keeps a full history of how their plans and data have changed over time. And the way that I do this is that when real world data changes, like let's say there's already some data in the warehouse from team X, and I'm going to load new data. I don't delete rows from the warehouse representing the data that is now wrong. I just change a flag on it and say that that row is no longer current. And then I create a new current row in its place. And so you can see that that's done with these three columns. And every fact table row in the entire database has these columns. The date, the effective start date shows the date time of the real world data that created this row. End date shows the date and time of the real world data that caused this row to be replaced or deleted. And if this row is still current, it's going to be a date in the year 99, sorry. And then there's a Boolean column indicating true or false, indicating whether this row represents current data. Now, in addition, there's going to be these two keys, created by and updated by key, which are foreign keys into the ETL batch dimension, indicating which import operation caused this row to be created and which import operation caused it to be updated and or like versioned off. You can traverse these rows to start with any fact in the warehouse. You can look at these rows to figure out what real world file sorry, what real world file caused this row to be created, as an example. So, end-to-end provenance for every piece of data. All right, so I think that that's the stuff that I really wanted to cover. This presentation was just an overview. These are fact dimensions and facts that I didn't cover today, but these are described pretty thoroughly in the core schema document. And I'm just going to show you an example of that. So this is this core schema document, and I don't know, it's like 30 pages long, but I'll show you something that we've gone over extensively. Like, so for example, here's where it's describing what a plan item is and how it looks in the warehouse. Or if I get down into here, let's see, here's an example of the time log. So for example, it's describing all of the columns in this table, what type they are and their interpretation. So you can see, for example, the delta minutes or interrupt minutes or current flag or the data block, etc. So so there's documentation on all of these different fact and dimension tables. So all of that is really useful information, and I've got the link here in the presentation. So I had a section here at the end that I was going to talk about ways to access it, but it's not strictly part of what we're going to talk about today, so it's something I can cover later.